Okay, so we are recording now. All right, so are there any questions or concerns pertaining to anything we've discussed so far? Does everybody sort of see how the algorithm works? Yeah. Okay. Anyone in the call who has any questions or concerns? All right, if not, let's start today's discussion. All right, so the first thing I want to do is I want to formalize the algorithm we discussed yesterday. All right, so at each step of this algorithm, what all do we have? And what is the minimum number of things we need to proceed? Yeah, exactly. We just need a dual feasible solution. From the dual feasible solution, we can do everything, right? So let's begin our, right, so it's going to be iterative. So let's start with our main loop. So, and what we have at this point is a dual feasible solution, y bar, right? So what shall we do now? What's the first thing we should do? Right, so let's construct the graph with zero slack. So let's say H is the tight graph, right? All right, and everybody knows what tight graph is. It is a graph which has only the tight edges, which means they are edges whose slack is zero, right? Just to remind you, the slack of an edge, UW, is the cost of the edge minus the dual values for the corresponding variables. Okay, so whenever the slack is zero, the edge is tight. UW is tight if slack is zero. So we construct this tight graph, which we can do easily because we have the dual feasible solution. And now what should we check? Does it have a perfect matching, right? So what we'll do is we'll call the we will call the perfect matching algorithm for bipartite graphs. And what this does is it either returns a perfect matching or returns a deficient set. All right. So if H has a perfect matching, let's call it M. In this case, what do we do? This is our, right, exactly. Return M and the y bar. Right? So the other possibility is that we have a deficient set. So else let S denote the deficient set returned by your perfect matching algorithm. Right, so this is a deficient set in the graph H, and our algorithm will make sure that S is a subset of U. Just to remind you, our input is GUW, right? And C is our cost function from the edges of the graph to the real ones. Right? And I'll also say G is V comma E, where V is U union W. Okay. All right. So if the graph does not have a perfect matching, the tight graph, then it has a deficient set. So we take this deficient set, and now what do? We compute the beta. Okay, so the beta is going to be the minimum slack of all edges UW. So these are edges in the original graph G, right? And what we want is, we want U to be in S and W should not be a neighbor of S in the graph H. Do you agree? This is exactly what we did yesterday. We wrote down W is in the neighborhood of S in G minus the neighborhood of S in H. That is the same as saying it's not a neighbor in H. Okay. So this is going to be our beta. And now what shall we do? Update the Y values. And how are we updating them? For every vertex U in S, so maybe I'll just be more precise. For each U in S, we are updating its dual variable to the original dual variable plus beta. Right? Oh, I think I'm running out of space here. Okay, no problem. Let me just switch it to single line. All right. So YU bar is YU bar plus beta. And for each vertex W in the neighborhood of S in the graph H, we are subtracting beta. Right? And that's it. We have done the dual update, and now we repeat the graph with the new tight graph, blah blah blah. Right? So this step here is the dual update. Okay. All right. So that's basically our algorithm. We just need to initialize. And how are we initializing? Right. Half of the minimum, right? So in the beginning, we're just going to say for each vertex of the graph, we set y bar v to be the minimum half of the minimum of the cost of all edges. Is that right? Okay. So we start with a dual feasible solution and we look at the tight graph and we repeat this loop until we are done. Okay. So it's actually a very straightforward algorithm compared to even the algorithms we've seen earlier. They were more complicated, I think, than this. Of course, this description simplicity comes at a cost, which I want to discuss now. All right, so let's try to understand what's the time complexity of this algorithm. Right, so let me see. Yeah, I think we can continue in the same note. Yeah. Yeah, so let's just continue here. Right. So let's consider the following question. So one of the things we are doing inside this loop, notice that the most expensive thing we are doing inside this loop is calling the perfect matching algorithm for bipartite graphs, whose complexity we have not discussed yet. But you can see that already all the other steps are very straightforward, right? Because once you have the deficient set, you just look at the edges, right? And compute the beta and then subtract beta, add beta. Those are very simple steps. So it's already clear that this part here must be the most expensive part in this algorithm, calling the perfect matching algorithm for bipartite graphs. So if we know its time complexity, and we know how many times this loop runs. If we have an upper bound on the number of times this loop runs, then we essentially have the time complexity of the whole algorithm. Everybody happy with that? All right, so we'll discuss that later, runtime of the perfect matching algorithm for bipartite graphs, because we didn't do it earlier. But let's just first talk about how many times does this loop run. So maybe I'll just put the question here. Can we upper bound the number of times, number of loop iterations? Right? So I think yesterday I said somewhat hastily that it's clear that it terminates. The problem is, if you have arbitrary real numbers, it's not that easy to see that you will eventually arrive at the optimal, right? You could be incrementing very gradually. So let's consider rational numbers. And the truth is, for most real world applications, you don't need all real numbers. You just need the rational numbers. Okay. So we're going to focus on rational numbers for now. And then we will see a different version of the algorithm, which actually does not rely on these assumptions at all. But that we probably won't do it today. So okay, so let's try to get an upper bound when all the costs are rational. Okay. In fact, I'm going to make a stronger assumption, and then we'll use that assumption for rational numbers. Let us assume that all the numbers we are dealing with are going to be integers. Well, that requires the costs to be even integers, because the original y bar is half of the minimum, right? So let us first assume that all costs are even integers. Okay, just for the sake of simplicity. If all the costs are even integers, then the first dual feasible solution is integral. This implies that initial y bar is integral. Okay, let's think about what the algorithm is doing. We are computing the slack. What is the slack? It is the cost minus the y bars. The cost is an even integer, y bars are integral, so the slack is going to be integral. And that is, the minimum is going to be our beta, so that's an integer. And then we are adding beta and subtracting beta from integers. So we will again have integers, right? And okay, then this implies that all y bars are integral. Okay? And this implies in particular that beta is always an integer. And remember, beta is at least 0, therefore beta must be at least 1. So at each step, we are incrementing the dual feasible solutions value by at least 1. Right? And that just proves that you will terminate in a finite number of steps. Let's actually get a bound. So, right. So remember that the dual is a maximization problem. The primal is a minimization problem here. So the sum of the y bars is always going to be less than equal to the cost of a minimum perfect matching. Right? This is just the equivalent. So this is for all the y bars. All right. And so if let's assume that n is a minimum cost perfect matching. Remember, we are assuming that the graph has a perfect matching because we can just run the perfect matching algorithm in the beginning. And if it doesn't have a perfect matching, then we don't even need to worry about this algorithm, right? So we are assuming that the graph has a perfect matching. All right. And the initial y bar, if you think about it, it is basically half times minimum cost of all edges. And we are summing over all vertices. So we get n over 2 times the minimum cost of all edges, where n is the number of vertices, right? Value of initial y bar is n over 2 times the minimum cost of all edges. Let's call this value L. Okay, so we are starting at some L value dual feasible solution, and at most it can be C cost of the minimum cost perfect matching, right? So that means that we have at most this cost minus L number of iterations. Does everybody agree? Okay, so that's when all the costs are even integers. Well, if all the costs are not even integers, then they are some rational numbers. But then you can multiply them by some gamma and make them all even integers, right? So now suppose that the costs are rational numbers. Right? So there exists a big enough integer gamma such that gamma times the cost vector is integral, right? And if you simulate the algorithm on after multiplying by gamma, it's going to do exactly the same thing, right? So the number of iterations simply multiplies by gamma, right? So in this case, we will have at most gamma times cost of the matching minus L number of iterations. Okay, whatever gamma is, it depends on what rational numbers you have. Okay, the point is it will terminate, right? Because there is a certain value of gamma, cost of m minus L is a certain value. So the point of this discussion is that the algorithm will terminate in so many iterations, and the time complexity will be big O of this times the complexity of the perfect matching algorithm for bipartite graphs. So maybe I'll just make a note here. Okay, let me erase this. So time complexity is order of gamma times the cost of the minimum cost perfect matching minus L times the time complexity of the perfect matching algorithm for bipartite graphs. All right. In particular, this proves a certain proposition 3.14 in the text. If the costs are rational, then this algorithm terminates. Okay. All right. Are there any questions or concerns at this point? Yeah. Can we prove that? But even if the edge graph doesn't repeat, we notice that some tight edges could stop being tight. I see. But you're saying that the edge graph should not repeat. Is that immediate? Like I kind of agree, but it's not immediate how I would prove that. But will that preserve the minimum cost perfect matching? Is it clear that we can do that? Right, it would need a proof. Yes, if you can get a lower bound on beta, then you're done. Right. That's actually the main point. Can we get a lower bound on beta? So yeah, actually I don't know. I also thought about these things and yeah, go ahead. Slack. Right. Mm. Yeah, if you can show that that set is finite, then you'd also be done. Right. So it's not immediate. That's all I'm saying. So it's not immediately clear how we can get a lower bound on beta. Right. If we can get a lower bound on beta in any way, then you would actually be able to prove it for all real numbers. So yeah, I don't actually know. So here is the open question that the text doesn't answer. And as I said, I'm not an runtime person. I generally am happy with a algorithm that's better than the naive algorithm, right? Um, so there is a question here which should be acknowledged. Is it possible to analyze this algorithm in a way that proves that it actually terminates for all real numbers? In fact, I would even say one more thing. Is it possible to come up with an analysis for this algorithm that shows that this is polytime and does not depend on the costs at all? So that is the thing that actually the text doesn't answer. They say that this analysis does not show polynomial time runtime, and that makes me wonder if there is a better way to analyze this algorithm that actually proves that it is polytime in the number of vertices or the number of edges, which is just n square maximum, right? So number of vertices is good enough. Looks like that, yes. But I'm still not convinced entirely that. Right. So that is what we will see. We will see that in the next lecture. But even this particular algorithm, it's not entirely clear to me. So here is the thing I have in mind. Supposing this graph H that we are constructing. So we know that certain edges that were tight stop becoming tight. And that is the big problem here, right? If we can show that the number of tight edges keeps monotonically increasing, or rather, more precisely, an edge that is tight will never become non-tight in a future iteration. If we can even show that much, then we would be done, right? But the thing is, that's not true. So my question is, can you show something like, if you look at the H graphs, the cardinality of the maximum matching does not go down. So rather than looking at the tight edges, I am thinking about the cardinality of the maximum matching in the tight graph. Can we argue that that does not go down? I am not able to find a counterexample. So in fact, I'll put it to the do it, try it yourself problem. Um, so yeah, it's a question that I have in mind and I don't know, I haven't gotten the time to answer it. So I'll just give it to you. Um, can cardinality of maximum matching in H go down from one step to another step of the algorithm, right? So you look at one iteration and you look at the next iteration. Can you find an example where the size of the maximum matching in H goes down? Yeah. Right. That would also be good to know. That could also help us. Okay. Right. So I should repeat for the people who are in the talk. So what Ravi is suggesting is it possible for some set that was not deficient to become deficient in a future iteration? Is that right? Yeah. So that would be another interesting point. It's another try it yourself problem. Yeah. Right. Right. I see. Okay. Okay. So maybe you can try to construct a concrete example and see what works. That's is it possible for a set that was not deficient to become deficient? Right. So I'm not writing them in full detail here. I'm going to put it in Piazza. So we are saying that going from one iteration to another, can some set that was not deficient in the first iteration become deficient in the second iteration, right? So these kinds of questions and their answers could help us in getting rid of the dependency on the cost, or in getting a termination theorem even for all real numbers, right? The truth is that we are going to see an algorithm that does not depend on the cost at all. Okay, so once that happens, this algorithm will be less interesting. But I do still think that this algorithm is very nice because it shows you the bare mathematical essential properties, right? And a more complex algorithm is always a bit harder to wrap your head around. Are there any questions among the live audience? I think there's a comment, so let me just see. What if the values are okay? So Anand, I think you asked a question. What if the values are irrational numbers? But I think we have already. Are you there? Okay, maybe your yeah. Okay, I can see your message. Yeah. So if the values are irrational numbers, then at this point we don't have an argument to show that the algorithm terminates. It looks like it should or it might, but we don't have a way to prove it right now. Right? At least I don't see how to prove it right now. So if you get an argument that works for all real numbers, then please do share with the others on Piazza. Of course, this algorithm, as I said, is going to be superseded by another algorithm where the dependency on the cost will be completely eliminated. It will depend only on um, the number of vertices. Okay, so at that point, one may not care that much for this algorithm, but it's still interesting for the sake point of curiosity. All right. Any other points? All right. So maybe I'll put some things on. There's another try it yourself problem here, I guess. Um, can we prove proposition 3.14 without the assumption that all costs are real numbers? Okay, so that is the one of the main questions we are unable to answer at this point. All right, so we will see that other algorithm in the next lecture on Monday. For now, I just want to go to the perfect matching algorithm for bipartite graphs and look at its time complexity. All right. Okay, so let me see. Maybe I should go back to that note, that document. And I think I have to share it again. Okay, so I have shared a different screen now. Okay, so let's try to analyze this algorithm here, right? Let's try to understand the time complexity of this one. Okay, so this is what we are discussing now. Okay, so let's just try to go through this algorithm quickly again, right? So at any point of this algorithm, you have a certain matching, you have an M alternating tree with respect to that matching M, right? And what are we doing? We are going to look at the edges which are going from the um, vertices of the tree in the U color class to outside the tree, right? And we look at these vertices. If we find an M exposed vertex, we get an augmenting path and we increase the size of the matching. Otherwise, we include this vertex in our tree and we extend the tree. We make the tree bigger, right? And right. And if we don't find any such vertex, then we just find a deficient set. All the U vertices in the tree, they comprise a deficient set, right? Okay. So I claim that at any point of the algorithm, either the size of the matching increases, and if the size of the matching does not increase, then either the size of the tree increases or you find a deficient set and the algorithm terminates. Okay, so these are the two main claims. Let me just write it down on the next page. Right, so we are discussing now the perfect matching algorithm for bipartite graphs, right? We have no costs here. Properties. The first property is that the size of the matching never decreases, right? Either it increases or it remains the same. And secondly, if the size of the matching does not increase in some step, then either the number of vertices of the tree will increase or the algorithm terminates with a deficient set. In fact, I want to change the notation. I call the deficient set D, and I think I don't like it anymore. I'm going to call it S. Okay. All right. So those are the properties of the algorithm. And based on this, we can actually analyze the runtime, right? Does anybody see what it is? Right. Right. Yeah. It will be what? Or in just n square, because the size of the matching is at most n over 2, right? Right. So we can get an order n square bound. But yeah, what you said is essentially the argument, right? So basically what you do is you consider each step of the algorithm where the m remains the same, right? So if the m remains the same, the size of the matching remains the same, well, then how much can you increase the deficient set? Well, it's a set of vertices. So the best you can do is order n, right? So for for all steps where cardinality of M remains same, we have order of n iterations of the loop, right? And well, the cardinality of the matching is at most n over 2, right? And so this is also going to be order n, right? So for all of these steps, we have at most order n iterations within that step, right? That's one way to think about it. So that tells us that this algorithm well, let me just state it clearly. The time complexity is order n squared. Right? So you see the difference. Of course, there are no costs here, so you don't expect cost to feature in the complexity. And the time complexity depends solely on the number of vertices. In the other one, however, it also depends on the specific costs, which are arbitrary real or rational numbers depending on your application, right? Well, we only did it for rational numbers. So when you assume that the costs are rational, you have a time complexity that depends not only on n, but also on the specific costs, right? And what we want is to get rid of that dependency on the costs. We want an algorithm for minimum cost perfect matching in bipartite graphs that depends only on the number of vertices. So we'll get there. Here is the plan. Rather than calling this algorithm every time in that algorithm, we are going to do some sort of a bootstrapping mechanism. We are going to integrate the two algorithms into a single algorithm for minimum cost perfect matching in bipartite graphs. I'm not going to do an example or the formalization today. I'll do it on Monday, right? But I'll just want to make one point here. So I'm going to look at our previous algorithm, and I'm going to call a certain part our subroutine that we will be using in the next lecture on Monday. So this entire loop is going to be our subroutine. Okay, let me see if I can copy paste it to the next page. Let's see if this works. Anyways, it doesn't matter. I'm just going to do it. I'll make a copy for the next lecture ready already. So this is going to be our subroutine. I'm unable to select it and copy paste it. So what does this subroutine do? This subroutine takes a matching and an alternating tree with respect to that matching, right? And it does three possibilities. Either it increases the size of the matching, or it increases the size of the alternating tree, or it returns a deficient set, right? So those are the three outcomes. Let me just say what are the inputs and what are the outputs. So this subroutine, the input is it's going to be the tight graph when we go to our minimum cost, right? So it's going to be a tight graph H, it's going to be a matching M, and it's going to be an alternating tree T with respect to that matching. Okay. And what are the outcomes? Let me not say output. There are three outcomes. The first outcome A is either the size of the matching increases because you found an M augmenting path using this alternating tree, right? The other possibility is that you added more things to the alternating tree. So the size of the alternating tree increases. And finally, the third outcome is that you get a deficient set. Okay. All right. So what we'll do then in the next lecture is we will use this subroutine and combine it with our minimum cost perfect matching algorithm for bipartite graphs and get a more complex algorithm. Although more complex, its time complexity will not depend on the actual costs of the edges. It will depend solely on the number of vertices. Okay, we won't need any assumptions about rational numbers or anything. All right, so that's the plan for Monday. And yeah, I just don't think we have enough time to do any example today, so let's not get into that. And on Wednesday, we will start with uh, perfect matchings in non-bipartite graphs. And I think it's a good thing because you will have time Monday and Tuesday to make sure that you completely go over the bipartite stuff, because non-bipartite stuff is way more complex than this. So it's good to have a grip on all of this. In the non-bipartite case, I think I'm going to ignore the time complexity and just focus on correctness for the sake of conciseness, because I don't want this to go on forever either. Okay. All right. So that's all for today. Are there any questions or concerns? Okay. Anyone in the call? Okay. If not, I'm going to stop recording.